Kind of fun. They tried to charge you $15 a night for Wi-Fi. Oh yeah. $60 water bottle. Sure, but if you like open the bottle, it's very. Oh yeah. It was right on the roof. $400 a night. I'm like, you know, the bar is probably the last. I still see it. Also, better like get off. Like
Worried about
Hello.
Introduce you today.
Okay, cool. It's all your, yeah.
If there are any quarterback updates.
Okay.
I think we're probably good to go. A lot of people are zooming in.
Okay.
So they're getting a head start on this.
Yeah, yeah.
Moving from Colombia to Guatemala. Out there.
All right, hello everybody. Happy Friday again. Happy free spring break. Whatever you want to call it. All right. So as usual, we'll get started with quarterback updates. Anything?
Afterwards, you take a bite.
I don't think there's much.
There are no updates.
No quarterback updates. Good, perfect. All right. I have the pleasure of introducing a wonderful faculty member of ours, Professor Yulin Pan. He is one of the introductory course teachers, NA 280. I believe you've all had him at this point. And then he also teaches some level regular courses as well. So
Thank you, Will. All right. Thanks for coming, everyone. So today we are going to talk about a brief history of fluid mechanics. Actually, I gave this talk about 2 years ago. I remember it was February 21st, 2020, before the pandemic. So time flies. And thanks for coming. Some of you might have heard about this talk before, and thanks for coming again. And for others, probably you haven't heard about this talk, but you may hear that this is pretty good from others. Well, don't trust them, because I don't want you to have too high expectations so that it sounds not that good. All right, so we are going to talk history of fluid mechanics. And fluid mechanics is a very comprehensive and interdisciplinary subject. And its development actually spans lots of tens of centuries. So it's actually very hard to put such a long history in a 1 hour talk. So what I'm gonna do is to select certain events and selective figures in this long development journey and try to reflect the very interesting and very grand development of this subject in the next hour. Okay, so let's start our journey. The first question, what is fluid mechanics? If you ask me this question, I don't know the answer. So if I have something that I don't know, I always ask Professor Wikipedia. So this is what Professor Wikipedia tells us. Fluid mechanics is a branch of physics that studies the mechanics of fluids and the forces on them. Well, this answer is so correct that it does not tell us anything. Essentially what it says is basic fluid mechanics is the mechanics of fluids. So that sounds a typical answer from Professor Wikipedia. So anyway, this is not good enough. So I asked another professor, Professor Goldstein from Harvard University. So the reason I asked him is because he wrote a review article on the development of fluid mechanics in the first half of the 20th century. And this is what he wrote in the review article. And he said, fluid mechanics are part of applied mathematics, of physics, of many branches of engineering, certainly civil, mechanical, chemical, and aeronautical engineering, and of naval architecture and geophysics, with astrophysics and biological and physiological fluid mechanics to be added. So this is much better. And from this answer, you see that fluid mechanics is some subject that can be applied to different engineering branches, with naval architecture to be one of them. And in addition to that, it can also be a part of applied mathematics and physics, and even pure mathematics. So what it tells us is that the fluid mechanics study can be either focusing on some very specific engineering application, or it can be very theoretical. And if you look at the fluid mechanics research today, you will find people studying some complicated ship flow, aircraft flow, or the blood flow. And you will also see people focusing on the understanding of the solution of one particular partial differential equation, or understand some particular turbulence spectrum. So it can be in both branches in terms of engineering application and the theory. Therefore, if we want to look at the development of the subject, we also need to split the development into two parts. And also divide its history into 3 stages. For the first stage, it is from the ancient world to somewhere like 18th century. Actually, spanning such a long time, the development of fluid mechanics in terms of theory is very slow. But in the meanwhile, actually, people have achieved a splendid engineering applications using fluid mechanics. And I provided 3 examples here. The first one is the so-called non-real water wheel that emerged in about 2000 BC in ancient Egypt. So as you see, this is an ingenious device that uses the stream power to do water lifting. And the second one is a Dujiangyan irrigation system that was developed in the Qin dynasty of China in about 200 BC. And so this is a basic system to deal with the flooding problem in the Sichuan province and also do irrigation in the meanwhile. So an amazing fact is that this project is actually preserved very well, and some part of it can still be used even today after 2,000 years. And the third one is a Zhenghe treasure ship that was built in the Ming dynasty of China about 15th century, 15th, 16th century. So it was basically a fleet with many ships, and the largest one is over 100 meters built by wood. And that is on the scale of an aircraft carrier, but that basically reflects the great achievement in the naval architecture, making use of fluid mechanics concept. So as I said, in the meanwhile, the development of the theory is pretty slow, but there are still some very meaningful events here. So the first person I list here is Archimedes, the lever guy or the showering guy here. Showering guy here. So I think you probably all heard of his story of the discovery of buoyancy principle when he was taking a shower, and he used that to help the king to measure the density of the coin. So I'm not going to elaborate on this story today. And second one, Leonardo da Vinci. You probably heard of his story of drawing X and drawing Mona Lisa. But in addition to that, he's actually also a great engineer, mathematician, and a scientist. And in his drawing, his paintings, you can find some drawings of fluid flow, actually. So these are 2 typical examples. The first one is for flow, go across the channel with varying cross section, and second one is for flow, go across the bluff body. And what is amazing from these drawings is basically you can see that there are some vortex in the drawings that are basically the very important element for the modern fluid mechanics that was developed maybe 400 years later. And you also see that probably he had some concept of turbulence because you see the fluctuation of the streamlines in his drawings. And the third one, Blaise Pascal, he's known for the Pascal's law, which tells us that the pressure in the still fluid transfer to all directions with equal magnitude. And he did a famous experiment, the experiment of the barrel. What he did is basically to put water in the barrel, and then he put a thin pipe on top of the barrel where the water are connected, and he keep adding water to the pipe, and eventually, because the hydrostatic pressure is very high due to the high water level, and the pressure transfer to the wall of the barrel and makes the barrel burst. So this kind of Pascal's law is used in lots of the machines today. And the fourth one is our say god of physics, Sir Isaac Newton. And you all know Newton has a series of books called Mathematical Principle of Natural Philosophy. If you look at the second volume of that, you'll find lots of study on the fluid mechanics. But unfortunately, many of these studies are not correct or not very exact. For example, Newton tried to estimate the speed of sound, but the result is it's different from the true result for a factor of √2 or something. I think David probably knows that. So anyway, but Newton has a great contribution is that he identified the property of the fluid viscosity. So what is fluid viscosity? So let's say we have some fluid between two plates, and the top plate is moving with velocity u, and the bottom plate is stationary. If we do this, basically the two plates will feel some shear stress in terms of feel some friction. So that is caused by the fluid viscosity. And it turns out that the shear stress can be computed by a constant, which is or viscosity constant times the gradient of the velocity. And this is the concept of the fluid viscosity that is discovered by Newton. And later, this type of fluid which satisfies this relation is named the Newtonian fluid. Okay, so next stage is from the about middle of the 18th century to the end of the 19th century. And a great feature of this stage is that we have the introduction of mathematics into the fluid mechanics. So you probably feel that with the introduction of mathematics, the fluid mechanics becomes more beautiful and more applicable. But actually, the situation is in the opposite direction. The introduction of mathematics results in a great rupture of the theory and engineering application of the fluid mechanics. And the culprit of this rupture is this guy, Jean D'Alembert. He's in fact a great mathematician, and he's also a guy with lots of opinion, and he has the courage to make fun of Newton. And he said, Newton's research is basically research of a pure curiosity, not applicable to nature. That is his word for Newton's research on fluid mechanics. And he said, what I'm going to do is that I'm going to use mathematics to study fluid flow. And but he doesn't know any governing equations about fluid mechanics. So what he does is, okay, I'm going to make some assumptions. I'm assuming that flow does not have viscosity and it does not have flotation. So I'm going to do something called potential flow theory. And he used potential flow theory to measure, to calculate the drag of a bluff body when the flow goes with a uniform speed. And he finds that all the drag is equal to 0. That is all, of course, opposite to our life experience, and that will be so that becomes his famous D'Alembert paradox that puzzles humankind for 150 years. And the second one, the great Leonhard Euler, he developed some other equation which actually already considers the rotation of the flow, but still he cannot add the viscous effect to the flow. And this set of equations is called Euler equation. It governs all the fluid motion without viscosity. And eventually, about another 100 years ago, at 1845, so this is a milestone day for the fluid mechanics. Naval and Stokes write down the Navier-Stokes equation, which governs the real fluid motion. So the equation looks like something of this, and it basically governs all fluid motion. It can be the water wave or flow around the ship, or flow around the plane, or blood flow. Every kind of flow that you can find the answer from the Navier-Stokes equation. So you probably think that with the discovery of the Navier-Stokes equation, the fluid mechanics becomes easy. But again, it's the opposite situation. And the reason is that this equation is too hard to solve. So I need to define what I mean by too hard to solve. So you can, nowadays, of course, you can put it in a huge computer and you can put a CFD program to solve this equation for applications. The true problem is that this equation is too hard in identifying its mathematical properties. So that problem actually caused lots of our difficulty in understanding fluid mechanics. In fact, this problem is so hard, and when it becomes one of the millennium mathematics problems that was proposed by the Clay Institute of Mathematics in the year 2000. So there are 7 problems, and this is one of them. And also, if you solve one of them, you get $1 million. If you solve 7, you get $7 million. One of them was solved, but this one is still not. So what is this problem? So this problem basically says that you need to prove the well-posedness of this equation, or you need to prove that it is not well-posed. to put in humans language, it basically says, if I give initial condition for this equation, you look at the solution. If the solution blow up, then it's not well posed. If the solution always not blow up, then it's well posed. Okay, so this is a problem that was proposed, and you can solve. If you can solve it, you get $1 million, but nobody solved it so far. So speaking of this, I can tell you a story. When I gave this talk last time. So after this talk, one student came to my office. I think he's not here. So he asked me, hey, Yulin, how about our whole department? We don't do anything for the next year. We just try to solve this. Can we solve it? I said, damn no. And then he said, how about our whole university? I said, still, damn no. And he didn't continue. If he keep asking me, how about the whole humankind? I will probably hesitate a bit, but if I want to take a bet, then still no. Okay, anyway, this is a very difficult problem. And the last thing I would like to add to this stage is actually an experiment by Osborne Reynolds. And what he did is basically to look at the flow pattern in the channel. And he found that at some certain condition, the flow actually becomes from the laminar flow to the turbulent flow, from very organized streamline to a chaotic pattern. And all this transition is dominated by some very important non-dimensional number called Reynolds number. Okay, so we'll come back to this later. And in the same period, the engineering applications actually grows a lot. And here you see the British propeller, you see the Dutch windmill, and you also see the Wright brothers flight, which are all developed in this stage. And it's worthwhile to know that for the Wright brothers flight in 1903, actually, people still haven't solved the Dalton paradox, and the wing theory has not been developed. So you have to admire the capability of the engineer to do things. Okay, the last stage from the about 20th century. So the in terms of theoretical development, this stage we call it modern fluid mechanics. And the starting point of modern fluid mechanics is Ludwig Prandtl, who is known as the father of modern fluid mechanics. And the reason for this is because he proposed and developed the boundary layer theory, which eventually solved the D'Alembert paradox. And the second one, Theodor von Karman, who is actually a student of Prandtl. And you probably heard of common vortex, which we are going to elaborate later. And he also worked a lot with the US Air Force, and he did lots of contribution for rocket and aircraft. And third one is actually a Russian mathematician, Andrei Komgarov. His biggest contribution in terms of fluid mechanics is in the turbulent theory, and he developed something called turbulent cascade model in 1941. That is probably the most important theory in turbulent flow. And the last one I included here is George Batchelor, and he's in the University of Cambridge, and he wrote a book on the homogeneous turbulent theory in 1953. And he's also the founder of the Journal of Fluid Mechanics, which is the most influential journal in the field. And of course, in the engineering applications, it really grows very fast. And here we have the NASA rocket, we have the modern weather forecast, which is in fact the simulation of a huge fluid system in a supercomputer. And we have submarines and everything developed. Okay, so this is a very long history with many, many things happening. So how do we go through this using a very simple example? And in the meanwhile, help you understand things. So what is a good example? I figure out probably this is a good example. So this is basically a very simple flow problem for some flow with uniform inflow velocity u and viscosity gamma past a cylinder of diameter d. Okay, simple enough, right? So the question here is basically, what do you think the fluid flow looks like for this very simple problem? So any ideas? So first question, to be more specific, will it be symmetric on the upper and lower surface of the cylinder? Symmetric around the center line? Or in other words, do you think the flow looks like something of this? No? How about something like this? We sort of, something like this, or something like this, or something like this. So which one is correct? Will you have answer?
The third one?
Sorry?
The third one.
The third one? Okay, that's a good answer. Yes, sometimes it behaves like the third one, but it can also vary. So in fact, this is a very difficult problem, even though it looks very simple. If you heard about the factory talk, which occurred on this Tuesday, it's basically an advanced version of this problem, and it's still studied today. So what we are going to do is that let's go to the history and look at how people think about this problem. Okay, so let's go to D'Alembert's error. So this is what D'Alembert thinks. He said, okay, I'm a mathematician, and as a mathematician, I would like to study this problem using mathematics. So what I'm going to do is that I'm going to neglect fluid viscosity and vorticity, because if I do that, the equation is more simple. It's much easier to solve. So he did that, and he wrote down the Gamma equations. So the Gamma equation is basically something like this in terms of potential flow theory. It is indeed much simpler than the Naval-Stokes equation as you have seen before, right? It's just a Gamma equation in the Laplacian form, and they have a boundary condition which says the fluid flow does not penetrate into the cylinder. And then he said, okay, this is very simple. I can definitely solve this problem. It's just a boundary value problem. I can definitely solve it with my mathematical talent. So he went ahead to solve the problem and find the fluid flow. The flow field is like this. So it's a very beautiful flow field, and I believe that he was proud of this for some time. So the streamline is denoted by these white lines here, and the color contour shows you the pressure distributions. So it's a pretty beautiful flow field, but is there any problem for this solution? So what is the problem here?
It ignores viscosity.
Yes, it ignores viscosity, and because of that, what happens? So actually, there's no viscosity. So the force on the cylinder is actually only from the pressure force on the cylinder, right? And because the flow is completely symmetric, the left side and the right side are completely symmetric. So the pressure distribution is also symmetric. So that basically means you do not have any force on the net force on the cylinder when the flow passes the cylinder, right? So D'Alembert said, okay, this is not right, because in reality we always feel some drag when the wind passes a car or something, right? Of course, they do not have a car at that time. So what he did is that, okay, maybe this shape is not the right shape. I'm going to calculate for different shapes. So he calculated the potential flow problem for different black body shapes, and he always finds a zero drag. And then he was surprised and said, okay, there's no drag. So he basically, he says a famous statement that when the fluid flow go across a black body with uniform speed, there is no drag. So this becomes the D'Alembert paradox that puzzled people for a very long time. Okay, all right. So here's some comment for this part of the history by Sir Cyril Henshewoods. He's actually a Nobel laureate in chemistry. And when he looked at this part of history, he said this. He said fluid dynamics were divided into hydraulic engineers who observed things that could not be explained, and mathematicians who explained things that could not be observed. Okay, so in some sense, this is still true today, but it's definitely a very good reflection of the state of fluid mechanics at that time. And I made up this. I think if D'Alembert hear about this, he would say, so what? At least I got famous paradox named after me. What do you have? With his attitude that he had the courage to make fun of Newton, he would say something like this. Okay. Anyway, up to this point, probably you are pretty disappointed by the potential flow theory, right? It can even not predict the drag. So the question here is potential flow theory useless or not? Okay, to answer that question, I would like to ask you a question. Okay, the question is, can you answer this? Why can airplane fly? right? So where does the force come from? If I have a wing like this, where does the lift force come from? So why can airplanes fly? So any ideas? Will you have an idea? Yes.
Pressure differential.
Yes, but where does the pressure difference come from?
The shape of the wing.
Shape of the wing, right? Okay, probably that everyone agree with him. Yeah, that is also what I learned in my high school. Okay, so this is the theory, right? It's basically says that we have a longer path on the upper surface and we have a lower path on the lower surface, right? We have a shorter path on the lower surface, right? And then for the air molecule to travel from the trailing edge to leading edge, if they travel in the same time, then they have to travel with a faster speed on top because the distance is longer. And they have to travel with a smaller, they have to travel with a smaller velocity on the bottom because the distance is shorter, right? For them to reach the trailing edge together. And because of that, I have a high velocity on top, meaning low pressure, and I have a low velocity on the bottom, meaning high pressure. And then I have a pressure difference, which gives us a drag, right? Is this correct? I see some people say no. So why is this not correct? So anyway, this is also what I learned in my high school. Well, I didn't see this is wrong, but actually NASA said this is wrong. This is actually the incorrect theory posted by NASA to explain where the lift comes from. Okay, so why is this wrong? This is probably the theory we learned in high school, all of us, still today. So why is this wrong? So to answer this question, I'm going to first show you an animation of the fluid flow around the wing or around the hydro or airfoil. So what you see here is that indeed we see a much faster velocity on the top than on the bottom, right? But the velocity difference is so large that it cannot be explained by the distance in the traveling distance theory, right? So then what is the right way to understand this much faster velocity on the top compared to the much lower velocity on the bottom? So to understand this, I create a simple way for you. So let's start from very simple problem that we have a cylinder as before, and we have fluid flow go across the cylinder, right? The flow field looks like something like this. And then what I'm going to do is to deform the cylinder until it becomes a wing shape. Okay, so I do a deformation, it becomes a ellipse, and the flow field is also deformed a little bit and becomes something like that, right? I do another deformation, it becomes a wing, and the flow field becomes like this. So what you see from here is that I have a stagnation point here at close to the trailing edge, and I have another stagnation point close to the leading edge, and this one is close to the trailing edge, but not exactly, right? So of course, this flow field does not look like the truth, which is like this, right? If you look at the truth, actually the fluid flow go past the trailing edge with equal velocity from the top and bottom. It does not look like that. So what we need to do is to do a correction on this flow field so that it looks like the truth. And so this is the what we need to do. So we take this flow field here, and then we need to add a correction. This correction is basically a circulation which goes like this, Okay, after I add this flow field with this correction of circulation, I get a flow field like that. And in this flow field, I basically have the condition that the fluid flow on top of the trailing edge and on the bottom of the trailing edge is the same. So it's a similar situation in this one. And this situation is called the Carter condition for airfoil or hydrofoil. Okay, now if you look at this picture here, oh, no power. If you look at this picture here, anyway, okay. If you look at this picture here, you actually will understand why there is a velocity difference, and the reason is because you have this circulation flow. On the top, it has a flow in this direction. In the bottom, it has flow in that direction. So that creates a velocity difference that eventually creates a lift force on the wing. Okay, So I don't know if any one of you have some friends in aerospace engineering. So go to ask your friends this question. All right, so let's summarize a little bit. Basically, we need the circulation pattern to create the true flow pattern for the whole problem. And actually, the circulation is very important in the computation of the lift, because as derived by Carter and Rukowski, the lift can be computed by the fluid density rho times the velocity u, which is the inflow velocity times the circulation of this flow pattern. Okay, so if we know the circulation, we know the lift on the wing. So I would say that this is the foundation of the modern aircraft industry, because you use this very simple theory, you can compute how much lift is provided on the wing. And one important thing is that all of these can be developed in the framework of potential flow. So now you can tell me whether potential flow is important or not, or whether it is useless or not. Okay, so I guess the answer is that it is useful, but we still haven't solved the D'Alembert paradox. So what should we do? Okay, so what will history do for that? So history provides a person called Ludwig Prandtl. He was born in 1875. And lots of things happened that year. And one thing is that the sewage system in London was first built. So that means we'll have a great person in fluid mechanics, which is Prandtl. Okay, he's known as the father of modern fluid mechanics. And the reason for that is because the boundary layer theory that was proposed in the year 1904. You probably know that the year of 1905 is a miracle year of Einstein, where he published 4 very groundbreaking papers. But actually, in the year before that, there's another groundbreaking papers on the boundary layer theory by Prandtl. So this is on fluid flow with very little friction. And Professor Goldstein wrote this comment on this paper, and he said this paper will certainly prove to be one of the most extraordinary papers of this century and probably many centuries. What does boundary layer theory do? Its idea is actually very simple, right? Let's say we have a plate, and we have a fluid flow go past the plate. So what Prandtl says is basically there will be a boundary layer that is attached to the plate and connect to the outer flow. In this boundary layer, we have a sharp velocity gradient. That velocity starts from 0 and it changes to the upper flow velocity on the top of the boundary layer. And because of this velocity gradient, I will have a shear velocity on this plate, so that this provides a drag, the answer for the drag. So in the Prandtl's situation, in the D'Alembert situation, since he didn't consider the viscosity, there's no boundary layer, so there's no drag. But now, when the boundary layer is proposed, actually the problem is solved. Okay, you might think that this is not a big deal, right? So everybody knows that even from Newton's age, we know that there is viscosity. So what's special about this? No, so I mean, you probably have thought about this when I told you about D'Alembert paradox. It's just a viscosity problem. Why does it take 150 years for people to realize this? So the reason that it's not that simple. The thing is that people know that if you have a finite viscosity, you will have a drag. But what if your viscosity becomes smaller and smaller, go to the limit of 0? In that situation, do you still have the drag? And the boundary layer theory actually answered that problem, but because if you look at his student, Prandtl's student, Paul Blasius's derivation, he basically said the boundary layer had a thickness of something like this. If you look at this formula, you will see that with the decrease of the viscosity nu, your boundary layer thickness also decreases. So that means if you reduce the fluid viscosity, this shear layer will have a larger gradient. Okay, so even if your nu goes to 0, you do not have a zero drag. It becomes a constant eventually. Okay, so that answers the question about, so that is why in Prandtl's paper it is called very little friction. So the boundary layer actually also works in this situation when your nu goes to 0. All right, so I can tell you a story about this. So when I learned this in a graduate school, in a class, the professor told us that I really hope that I have a student who is like Paul Blasius who can write down this kind of formula for me. Then I said, okay, but you need to become Prento first. Okay, I didn't say to him, I said that to myself. Okay. Okay, so now you probably think everything is clear. If you have a cylinder, basically I have this boundary layer that attached to every plate of the cylinder. So I'll have a shear stress on the cylinder that provides a drag, right? But there's still a difference for a cylinder compared to a plate, because for the cylinder, at the rear part, we'll have some flow that is in the different direction, the reverse flow, right? And because of the reverse flow, we'll form some vortex at the rear part of the cylinder. So what does this vortex do in fluid mechanics? Of course, Prento also realized this problem. So he asked one of his students, whose name is Carl, to investigate this problem. So what Carl did is to do some experiments. So he built a tunnel and he built a cylinder. He put the cylinder into the tunnel and do the experiments, right? And then he basically found that he didn't observe symmetric flow pattern. He observed some alternating flow pattern, as Will mentioned, right? And so Carl just went back to Prento and told him the phenomenon. And Prento said, okay, it must be your cylinder is not round enough. So Carl went back and made his cylinder round enough and do the experiments again, and still that happens. And then Prento said, it might be your water tunnel is not symmetric. So then Carl went back and worked on his tunnel and did the experiments again. But no matter what he does, he always sees the alternating flow pattern. Something like this. Okay, this is a movie. I'm not going to play it. I think something is wrong when I tested it yesterday. But it's basically something like this. So in the meanwhile, another student of Prento, which is von Karman, also saw all these experiments. So von Karman did something different. And he said, maybe the flow really should behave like alternative pattern. And he did some hydrodynamic analysis, and his conclusion is basically, if the flow is symmetric, it represents an unstable state, like we have a ball on the hill. If we add any perturbation, this ball will fall. So the flow is like that if it is symmetric. If the flow behaves like unsymmetric, something like this, and then it represents a stable condition that the ball is in this situation, so that it does not go unstable. And this analysis is definitely correct. It's not very precise, but it's definitely correct. And people realize that this alternative pattern is actually the nature of the fluid flow. And von Karman is also a very modest person, because when people said that he's the founder, he's the inventor of the Karman vortex, he always say, okay, it's not me. And because if you look at some painting in the church of Italy, you will see that people already draw this kind of alternate pattern on the foot of this person. And he said, people just know this long time ago. I just proposed a theory on that. But this is definitely a phenomenon that can be observed in many different scenarios. And here you see the Karman vortex behind the mountain. So this is a picture from real experiments in the lab, and this one is what is observed in the atmosphere. Okay, so this is the true nature of the fluid flow. And after that, actually, von Karman transferred to Caltech in US because he was previously a student of Prento in Germany. So he came to US and became a professor in Caltech, and he worked a lot on the rocket science and aircraft. He worked a lot with the US Air Force. And in 1961, he was 81 years old, and he became the first recipient of the National Medal of Science. And this is a letter by the White House, and this is what President Kennedy said in the awards ceremony. And he said, Dr. von Karman, it is a great pleasure for me to select you as the first recipient of the National Medal of Science. I know of no one else who more completely represents all of the areas with which this award is appropriately concerned: science, engineering, and education. So 2 years after this, von Karman passed away. He was unmarried for his whole life, but he's a very interesting person, and he has lots of story to tell people. So people like him a lot. And 2 years after the recipient of the award, he passed away. And at that in that year, actually 2 stamps were issued. One from U.S., this one, and the other one from his motherland, Hungary. So this one you see the carbon vortex, and this one you see the rocket as the background. Okay, so now let's go back to cylinder flow again. So probably now you think that we understand everything, right? So, but actually, if we look at the initial problem of all these patterns, in fact, all these patterns can happen. What we discussed about carbon vortex is basically this pattern, but all the other patterns are also possible under certain situations. So why is that the case? And the reason is basically all these states are actually solutions for Navier-Stokes equation at different parameters. So what are these critical parameters that determine the flow pattern? And that is simply called the Reynolds number, which I told you at the beginning of the talk. And for the problem, the Reynolds number is defined as velocity u times the diameter of the cylinder d over the viscosity of the fluid d. So depending on different Reynolds number, my flow can behave differently. At very small Reynolds number, it can be some relatively symmetric pattern. And then with the increase, I have some separation zone. And further increase, I have the carbon vortex. And further increase, the carbon vortex disappears, but I see lots of fluctuations of the flow. Okay, so then the question is about these fluctuations. So why do we have these fluctuations? In fact, this fluctuation pattern is called turbulent flow, which is one of the unsolved problem in or maybe it's only one of the unsolved problems in classical physics. That might not be true, but definitely one of a handful unsolved problems. Okay, so why is turbulent flow so hard? So, and another question is, what do we mean by unsolved? So what is unsolved for turbulent flow? Okay, so to explain this problem, cylinder flow is probably too hard. I need to start from something that is even easier, that is channel flow. Okay, so this is the famous experiments by Osborne Reynolds, and what he did is basically doing experiments in a fluid channel, and he had some device to control the flow speed in the flow channel, right? So when he increased the flow speed, basically increased the Reynolds number. So when he does that, he basically finds that when I increase the Reynolds number, my flow pattern will transfer from laminar to turbulent at a certain some Reynolds number. It just happens. So then the question is, I observe this in experiments, but why is that the case? So how do I understand that there's a transition from laminar to turbulent flow? All right, so here are some examples. The first one, oh, doesn't work, I don't know why. Anyway, the first one basically shows experiment. And in the experiment, when you increase the flow speed, you will see the streamline become the streamline become from a straight pattern to this unorganized and chaotic pattern. The second one is the experiment you can do in your kitchen with your kitchen faucet. Basically, with a small stream, that flow is very organized. But if the flow stream is larger, you will see lots of fluctuations of the flow. Okay, you can observe that in your kitchen. Okay, so the question is why that happens. The study of this problem started from the so-called Summerfeld School, which is founded by this person, Arnold Summerfeld. Okay, he's actually one of the founding fathers for quantum mechanics. Of course, he's also a fluid dynamicist. And he's also a great teacher because 6 of his students are Nobel Prize laureates, including Heisenberg and Pauli. But he himself holds a world record. The world record is that he's the person who was nominated for a Nobel Prize for most of the times. So you can take a guess how many times he was nominated for a Nobel Prize.
8 times.
Sorry?
Was it 8 times?
8 times?
Yeah.
That's too conservative.
50 times.
That's still a little bit conservative. He was actually nominated for 84 times,
Oh,
but he never got the prize.
No.
Yeah, his student, 6 of students, in contrast, 6 of his students got the prize. Okay, anyway, he wanted to solve the turbulent problem, right? So what he thinks is basically as follows. He said, okay, I have a velocity profile for this channel flow like this. And what I'm going to do is that I'm going to add a small perturbation on that velocity profile. And I look at whether this perturbation will grow or not. If the perturbation grows, then it will transit to turbulent. If the perturbation does not grow, it decays, then it remains steady. Then what I need to do is basically to find at what Reynolds number does this perturbation grow, then I understand at what Reynolds number it will transit to turbulence. Okay, so this is his thinking, which is not hard to follow. And based on this thinking, he wrote down this so-called Summerfeld equation, which basically governs the small perturbation. So if you understand this equation, you can understand whether this perturbation grow or not. So the remaining question is to find a solution for this equation and to solve the problem. But this problem is extremely hard. And Summerfeld spent lots of time and he cannot solve it. But he said, okay, I have great students and 6 of them are Nobel laureates. I will give the problem to my students. Okay, so he gave the problem to 3 of his students. The first one, Ludwig Hopf, and the second one, Fritz Noaza. You're probably not familiar with this person, but both of them are great mathematicians and physicists. And actually, they are both coming from some family of scientists. You probably heard of Hopf bifurcation in nonlinear dynamics. Well, that Hopf is his brother. And for Noaza, you probably heard Amy Noaza, who is his sister, that was named as the most important female mathematicians in the history by Einstein. Okay. All right. So both of them cannot solve the problem, and actually they try to prove that the Summerfeld equation is always steady. That is not correct in physics. So they both failed, and then Summerfeld said, okay, I'm going to give it to my most clever student, Werner Heisenberg. Okay, so Heisenberg is definitely a very capable physicist, definitely one of the top 10 in the history of our physicists. And so Summerfeld gave the problem to Heisenberg. So Heisenberg started to try to solve it during his PhD period. And he found that he could not solve it. But the deadline for defense was approaching, and he had nothing to do, but he said, okay, I'm going to guess a solution. So he guessed a solution for the Summerfeld equation and gave to the committee. But in terms of guessing the solution, I basically mean that he made lots of assumptions, which he doesn't know is correct or not, but he just solved that equation based on his assumptions. And during his defense, the committee doesn't know whether it's right or wrong. But since he's Summerfeld student, so they say, okay, you can graduate. And after he graduates, he didn't really come back into the turbulence problem. He went to study quantum mechanics and become the founder of the subject later. Okay, basically Heisenberg failed as well. So you can look at the attitude of Summerfeld from his own notes. So this is what he said in his own notes. In 1903, which is the starting of his, where he started to try to solve this problem, he said this: still, there is no precise theoretical method to determine the orbital velocity and the pressure gradient beyond the critical velocity. And then in 1906, when he worked a little bit on this problem, he said, maybe 3 years, he said, unfortunately, I still could not make progress with the problem to determine the critical velocity hydrodynamics. And then after another 3 years, he worked on the problem for another 3 years. He said, I have tortured myself continually with the turbulence problem and spent almost all of my time with it, but I could not accomplish it. After that, he gave the problem to his students. And then at 1923, he said, I could not have suggested a theme of such difficulty for a doctoral dissertation to another of my pupils. So basically, he gave up. There's another story about Summerfeld or Heisenberg, I don't know who, but when he was about to die, he said, when I see God, I'm going to ask him 2 questions. 1, why is there quantum mechanics? And 2, why is there turbulence? And I'm pretty optimistic that God will have an answer for the first one. Okay. So it's very hard, but eventually we have some breakthrough by C.C. Lin. C.C. Lin is actually a student of von Karman. And in his PhD thesis, he actually solved the problem with more rigorous mathematics. And he wrote the theory into a book, the theory of hydrodynamic stability. And in the same year, von Karman took C.C. Lin to meet with John von Neumann. So basically, John von Neumann is von Karman's friend's son, so they know each other pretty well. So von Karman said, so my student C.C. Lin is very outstanding. He solved the problem and he found that the critical Reynolds number is 5,773. So can you help confirm this answer? So at that time, people just started to use computers. So von Neumann actually took this problem to a team of computer scientists, and they verified that this is the correct answer for the Summerfeld equation. Okay, so this actually marks the ending of this problem. But if we go back to look at the Heisenberg solution, okay, even if he did something like a guessing and made some assumptions, actually Heisenberg's answer is very close to this number. After all these assumptions, and nobody understands. So you have to admire that his physical intuition in solving very complex problems. Okay, now another question, which is very hard for turbulence, is that when I have turbulence developed, let's say I'm above this Reynolds number, I have turbulent flow, then what can we say about this turbulent flow? Is there anything or general rule that I can apply to this turbulent flow and say that it always holds for turbulent flow? And this problem, there's no answer. So it's not solved yet, but the most close one is probably from Andrei Kolmogorov, who is a Russian mathematician. He's actually, I think, one of the most important mathematicians in the 20th century. Okay, so I can also tell you many stories about Kolmogorov, but we don't have lots of time. I'll just tell you one, okay? So when Kolmogorov went to the college, he actually majored in history. He was very interested in history. So as a sophomore, he wrote a paper to his history teacher. And the paper basically made use of some probability theory to explain some phenomena in the Russian history. And his history teacher didn't quite understand that. And he said, okay, Andrei, if you want to show your theory is correct in history, you need 10 people to say you are correct. So Andrei Kolmogorov was not happy, and he asked, in what subject, if I say the answer is correct, then it's correct. And his teacher said, go to mathematics. So he became a mathematician. So basically, his theory is not hard in terms of turbulent flow. Basically, what he thinks is this. If I have a barrel of water, I stir this barrel to create large vortices. And then this large-scale flow will transfer to small-scale flow to form an energy cascade. And as a result of the energy cascade, you can also observe a spectrum with a certain slope. So the spectrum is basically tells you how is the energy distributed in different scales. And based on his theory, you will have a parallel form where k is a wave number, you have a k to the -5 or 3 as your spectrum. So the theory is actually very simple. It does not involve complicated mathematics, mostly physical intuition. But this number of -5/3 has been verified by lots of experiments that this is indeed the case for the turbulent flow. Okay, and the last person, as we mentioned, is George Batchelor. So what he did is basically to further develop Kolmogorov theory and eventually end up with this book of the theory of homogeneous turbulence. So Batchelor is actually an Australian person, and in his undergraduate, he worked on nuclear physics, but then he somehow found turbulence is interesting. So he went to the University of Cambridge to study turbulence with G.I. Taylor and became a giant in the field. He's also a very aggressive person, and he wants to end the turbulence problem by him. But then he found that he's so naive. He cannot do that. And the reason is that later they find that the Kolmogorov theory, the K31 theory, is actually not perfect. It has flaws, so it does not govern all the turbulent flow pattern. So there are something very important called intermittency that can disturb this -5/3 number. And the intermittent pattern is still something that we don't understand for turbulent flow. So basically, George Batchelor gave up. But he did two other meaningful things, which make me think that maybe his giving up is a good thing. And one of the things that he founded the Department of Applied Mathematics and Theoretical Physics in Cambridge. And that later became the center of the fluid mechanics research. And lots of important persons are from this department. And second one is that he created the Journal of Fluid Mechanics, which is considered as the most influential journal in fluid mechanics these days. And people still publish a lot on this journal for the major results for fluid mechanics. Okay, it's almost at end. So what we did today is basically to review a number of important figures in the history of fluid mechanics. And you see all of them here. And the last one is Batchelor. But the question is, who will be the next one? Will that be one of you here? Okay, thank you. That's all my talk. I don't know if you want to ask questions or not. Yes, Will, you have a question.
What made you go through the history of fluid mechanics? Like,
What made me go through that?
yeah.
I'm interested in myself. That's why I just read books and summarize the things here. I do have a part 2, actually. Maybe I can do that later, but not today. If you are all like it, I can probably develop part 3. Yeah, Brian.
So in terms of like the most complicated things known to mankind, where would you put fluid mechanics?
In fluid mechanics?
Like, no, just in general, like compared to, I don't know, launching a rocket or something like that.
Oh, it's all complicated in different ways. Launching a rocket is different from solving the millennium problem. Both are very, very difficult. It's just difficult in different ways. I don't know what is the most difficult one. But definitely you see all kinds of difficulty in fluid mechanics. You see the difficulty of launching a rocket. You also see the difficulty in a very theoretical study. So, yes.
So then on the timeline, who do you think made like the biggest breakthrough in your opinion?
In my opinion?
Yeah. Could you say Archimedes at the beginning, or would you say someone closer to the end?
I guess Prandtl. If I pick one, might be Prandtl. If I pick 2, maybe, I don't know, Kolmogorov or von Karman. But Kolmogorov is actually a very well-rounded scientist. He works on a lot of different things. You guys learned the probability, and the axiom of probability is actually proposed by Kolmogorov. the 3 axioms that you can use to derive everything. So that is from Karmarov. Yeah. Well,
when you first developed the timeline, is there anybody you had to leave out purposefully or like didn't?
I just read things randomly and put them together. Actually, there is a journal called the Annual Review of Fluid Mechanics. In that journal, that's not only for fluid mechanics and science. There is also some review of a person's lifetime on that journal. So you can learn lots of things there actually. Okay, any more question or? Okay, thanks everyone. Yes, if you are interested, I can do part 2 later. Okay, yes. All right, thanks.
Thank you.